Hello, my name is Furkan Guc. I am a PhD student from the Merced at the Department of Mechanical Engineering, University of California, Merced. I am going to present our work, Digital Twins-Enabled Remote Laboratory Learning Experience for Mechatronics Education. The outline of the presentation is as follows. I will start with my introduction and the motivation of this work. And then I will present in-person laboratory design of ME142 Mechatronics course. Then I will introduce a novel design of digital twin-based interactive remote lab development for this course. And finally, I will present a case study for interactive digital twin development for motion controls. And lastly, I will end up with my results and conclusions. Let's start with the introduction. As an introduction, our motivation starts with engineering education and laboratory experience. In mechatronics and control, practical experience is required to understand how a complete mechatronics application is built. The COVID-19 crisis makes most universities worldwide close for in-person instruction and move into virtual education. Current virtual education requirements forced us to come up with a solution for enhanced mechatronics education. In this context, digital twin-based interactive mechatronics laboratory design enabled students to participate in remote practical experience. And the second part of the presentation is focused on ME142 mechatronics laboratory design. ME142 mechatronics is an upper division course offered in Department of Mechanical Engineering at the University of California, Merced. It consists of both theoretical concepts and practical methods for electromechanical systems. The course is lab-intensive with 2.5 hours of lectures and 3 hours of laboratory sessions per week, and it is offered annually each week. A total of 60 students are registered for taking the course at each term, which is a considerable number of laboratory experiences, coordination, and learning. Before COVID-19, the ME142 laboratory introduced an intensive hardware-based laboratory focused on developing real-time mechatronics application using low-cost open-source hardware and development boards. During last ME142 offering on spring 2020, the COVID-19 moved teaching into remote learning with half of the semester activities performed. And the remote instruction is still operating for the spring 2021 offering. In this context, providing access to real hardware for each student is not time and cost efficient. The key solution for the remote laboratories is leveraging novel technologies like digital twin to the service of education. Therefore, digital twin-based interactive remote laboratory design is proposed using flipped classroom model and modeling, analysis, and design methodologies. Since the access to hardware is not available by the nature of the remote laboratory design, the idea of digital twins was leveraged for the educational purposes. In the beginning of the course, a questionnaire is designed to understand the background knowledge of the students. Results indicate that most of the students have entry-level knowledge and skills for both theoretical and computational background. Throughout the design process of the remote laboratory offering, fundamentals of the engineering instructional laboratories are playing a key role in order to create a comprehensive laboratory curriculum. In this context, the learning objectives of comprehensive remote laboratory curriculum consist of instrumentation, models, experiment, data analysis, design, learn from failure, creativity, psychomotor, safety, communication, teamwork, ethics in the laboratory, and sensor awareness. Using these self-containing list of objectives, remote laboratories aim to achieve high-level hands-on learning tool in a mechatronics course. The emphasis of the remote lab design is focused on digital twin development. In this context, a self-contained framework is employed in order to develop a digital twin model in the ME142 laboratory. It is composed of 5 steps, each corresponding to target system definition, system documentation, multi-domain simulation, digital twin assembly and behavioral matching, and finally, digital twin validation and deployment. The details of each step are investigated in our case study. And the third part of the presentation is focused on the digital twin case study for the motion controls application. In the case study of interactive digital twin for motion control, target system is defined as the real-time velocity and position feedback motion control. In this context, system is composed of corresponding TC motor, Arduino Mega, Arduino Shield, and Hall effect encoder. Then the digital twin structure is defined in 3 different domains, namely digital domain, electrical domain, and the mechanical domain. The multi-domain simulation framework is created in Simulink Foundation. And as step 4, behavioral matching between a real physical system and digital twin is performed using Simulink design optimization tool. Electrical and mechanical parameters of the digital twin are initiated with the manufacturer values and optimized using data from the real system. And for the final step, digital twin is transformed into a web application using MATLAB App Designer and MATLAB Web App Server. Then the final web app of the digital twin is validated with the comparison of the real system. Finally, the final part of the presentation is focused on the results and conclusion. The results of the proposed remote laboratory design are delivered in 2 formats. The first format of the results is the digital twin library developed by the students of Spring 2020. Using this case study of digital twin development, students are expected to work on the groups of 6 as the final project. Each group are assigned to their own digital twin applications like ball and beam, temperature control, and the time level control. Finally, all applications are compiled and published in a web app server in order to increase accessibility. The second type of the results are investigated using pre- and post-course surveys. In the first week of ME142 Mechatronics course, students are asked to evaluate their own confidence levels in digital twin capabilities and relevance to control system design. As shown in the course survey results, overall confidence level of students are below expectations before the course. Then, in the post-course survey, students are asked to evaluate their confidence level for both before and after the course. Based on the comparison of the before-after the course and the increase in the overall confidence levels of students, the effect of the proposed remote laboratory design is measured. As the final summary and conclusion, a novel proposal for interactive mechatronics remote laboratory is presented. The learning experience is elevated using flipped classroom and MAD methodology. The laboratory program is designed to bring students from an entry to an advanced skill levels of MATLAB and Simulink to develop their own digital twin applications. Proposed remote laboratory design is applied for Spring 2021 offer of ME142 Mechatronics course in the University of California, Merced. The recordings are posted online at the YouTube channel of Professor Yang Chen, and the success of the applied laboratory program is measured through pre- and post-course surveys. Here, these are our references. Thank you all for listening.